Imagine a parking lot where the rate at which cars arrive depends on how full the lot already is. The arrival rate is no longer a single number. It changes with the state of the system. We write lambda sub k to mean the arrival rate when there are k customers already in the system. The classic formula, p block equals p sub l, secretly assumed lambda was constant. When it isn't, we need a smarter formula. Here is the fundamental building block. Consider an arc leaving state k with intensity lambda sub k. The average number of jumps per unit time along this arc equals lambda sub k times p sub k. The system spends fraction p sub k of its time in state k, while there arrivals happen at rate lambda sub k. For example, if we're in state 230% of the time, at rate 4 per second, that gives 1.2 arrivals per second from state 2. Now, picture the full chain. States 0 through L forward arcs carry state-dependent rates, lambda 0, lambda 1, and so on. The loop at state L represents arrivals that bounce off the door. To find the total rate of attempted arrivals, we sum the flows across all states from 0 to L. Crucially, we include state L. Those arrivals still happen. They are just rejected. The blocked arrivals are exactly those that occur in state L. That rate is a single term, lambda sub L times p sub L. Putting it together, the blocking probability is the ratio, blocked flow divided by total arrival flow. This is the true fraction of attempted arrivals that get turned away. A beautiful sanity check. If every lambda sub k equals the same lambda, the lambdas cancel, the probabilities sum to 1, and we recover p block equals p sub L. This is the pasta property for true Poisson arrivals. A printer is shared by 3 employees. Each idle employee submits jobs at rate 1 per minute. Service rate is 2 per minute. There is no buffer, so the system holds at most 1 job. Here is the chain. From state 0, all 3 employees are idle. So the arrival rate is 3 lambda. From state 1, only 2 employees remain idle. The third is in the system, so the rate is 2 lambda. Solving with the cut method, 3p0 equals 2p1. Normalizing gives p0 equals 0.4 and p1 equals 0.6. One might guess the blocking probability equals p1, that is 0.6, but this would be wrong. Minus arrivals happen more often when the system is empty, so arriving jobs see a biased view. Applying the correct formula, lambda 1 times p1 over lambda 0 p0 plus lambda 1 p1. That gives 2 times 0.6 over 3 times 0.4 plus 2 times 0.6. The answer is 1.2 over 2.4, which is exactly 0.5. Here is the deep insight. The system is full 60% of the time, but only 50% of jobs are blocked. Submissions are biased toward times when the system is empty. Closely related is the effective arrival rate, the rate of customers that successfully enter. We sum the flows only over the non-blocking states, 0 through L minus 1. This is what we feed into Little's law to find the mean time a customer spends in the system. To summarize, flow on an arc equals the rate times the time fraction. Blocking probability is a ratio of flows. When lambda is constant, the formula collapses to p sub L. Otherwise, arriving customers always see a biased view of the system, and that bias is precisely what this formula captures.